from the Institute of Science, University of Mumbai, and doctorate from Institute of Chemical Technology, Department of Physics, in the area of carbon nanotubes-based polymer nanocomposites. He has also worked earlier as a scientific assistant C in the National Center for Nanosciences and Nanotechnology in University of Mumbai, since he has an inclination towards teaching, and is currently working as an assistant professor in GM Khalsa College, affiliated to University of Mumbai in Matunga. And sir, we are really pleased to have today. The topic is quite different for most of us, and it's over to you, sir.
Introduction to material science from macro to nano. I am, as introduced, Dr. Arvind Singh, assistant professor, Department of Physics. I come from Guru Nanak Khalsa College, and it is one of the oldest college of Mumbai. It was established in 1935. Our great leader, Dr. Babasaheb Ambedkar, at that time in Mumbai, there were no colleges, so he had requested SGPC, Shri Gurudwara Prabandhak Committee, Punjab, to open an educational institute, and this was open, and this is view of my lovely college. So basically here, the talk will be in three parts. The first part will be we will be understanding what is material science, what is material engineering. Second part will be about what is the new thing in the material science, that is advanced materials and nanomaterials or nanotechnology. And third one, if the time allows, I will present few slides for the work which we are doing with computational based material science. Okay. So as the participants are from different backgrounds, I would like to go with the basics. Material science is study of classification of materials which can be organic, inorganic, and biological materials. So organic means the one which has organic material, like we have tissues or wood, plants. These are organic type of materials. Inorganic means metals or ceramics, all that. Biological materials, as I said, like tissues and all, they are biological materials, DNA, cells, or currently the coronavirus, all these are biological materials. We also have semiconductor materials, like the photovoltaic material, the solar panels, or the chips in our mobiles, laptops, and electronic devices. And current trends and advances in materials, material structure and examination, selection of materials. So in this, it is very important to know the crystal geometry and structure. The crystals, single crystals, there are many types, lattice points. These are the very basic physics coordinate, very basic physics things. So I will not go into detail of that, but understanding the material. I will try not to go with the physics point of view, but in a general way. So material science people also know that it is materials engineering. It is an interdisciplinary field applying the properties of matter to various areas of science and engineering. Like if somebody says, I want to work in making rockets. So rocket making is of multiple ways. Like you can work in what type of materials will be used for the painting the rocket surface, what kind of material will be made by the rocket will be made up of, which should be light, how it is made. It will be basically the aerodynamics and engineering part. So material science actually covers both science and engineering. This relatively new scientific field investigates the relationship between the structure of materials at atomic or molecular scales, and which in fact changes, or it is responsible for the macroscopic properties, like which paint we are using to the surface, which will actually define how much will be the weight, whether it will be able to pass through the Earth's atmosphere without burning and other. So all these are called as macro. Macro means big. We'll be talking about this, how big and all that later. But we can understand macro means I can see my fingers, my hairs, I can see, but I cannot see the bacteria or or the bacteria which are in micro size. So macro means something which we are able to see with our naked eyes, and which we are not able to see. They are of micro sizes, like 100 times smaller than the diameter of hair. 100 micron is the diameter of our hair. Now, with significant and media attention focused on nanoscience and nanotechnology in recent years, material science is becoming more widely known as scientific field of science and engineering. You must have come across various advertisements, like the Ajay Devgan and Kajol, the famous Bollywood celebrity couples. They have this Lifebuoy soap in which they say that there is a silver activated into this material. Then there are certain copper ions advertisement by Madhuri Dixit ji, which says that इसमें ions है, copper ions. So copper ions are basically in the nanoforms or ionic forms. Okay, and there are many more, like Chawanprash, Sona Chandi wala Chawanprash. In earlier days, people used to eat Chawanprash, so that was made properly by using that gold and silver. In that, the gold was in nanoform, मतलब 1,000 or 10,000 times smaller than the diameter of it. So it's not like something nanoscience or nanotechnology is new. Already we knew. we knew already, but with the advent of new technology, we are able to know them more. So let us see what was the history of material science. I'm not going to go show the diagrams of the old age people's olden or historic period men's and all, just few about the materials. So the material of choice of a given era is often a defining point. You can understand how important materials are. Even the age of human is defined by the type of materials they were using, right? So it was Stone Age, Bronze Age, Iron Age, Steel Age, and these are some good examples to know that how important material science is. A major breakthrough in the understanding of materials occurred in the late 19th century when the American scientist Joshua Willard Gibbs, known for thermodynamic study in physics or chemistry, demonstrated that thermodynamic properties related to atomic structure in various phases are related to the physical property of the material. This was a remarkable theory, a remarkable discovery or breakthrough understanding of how this is happening. To just make you understand, suppose we have chapatis made at home. If you want to check any material, we use X-ray, other techniques, materials, big scanning microscopes and all. But if you are making a chapati, your mother or at home, we are making chapatis. So we don't take an instrument and peep inside the chapati to see whether it is made or not. How the surface is now decides how much heat has passed into the inside of the chapatis, right? So this is basically thermodynamic properties related, how the material is forming and all that. And that is actually related to the atomic structure of the material. You will have good chapatis with maida, very flexible. You will not have good flexible chapatis, or you can say rotis with your jawari or bajri grains, right? They are different in terms of their atomic structure, in terms of their mate. So they will vary. The same way materials are also vary. You can see the powders of this jawari, bajri, or all this wheat or corn. They look almost not very similar, but almost similar. But you see, when the chapatis are made, they look so different. So this is actually what thermodynamic properties. So how the materials are going to behave, what are their thermodynamic, heat and dynamics, how the molecules, atoms, they move in certain or they behave each other. That is related to the structure property, which in turns, that is related to their various phases and then to their final properties, physical properties as well as their other chemical properties also. So the basics of material science involves relating to the desired and relative performance of the material in a certain application to the structure of the atoms and phases in that material through characterization. So whatever material we are taking, we are doing, then we characterize it, right? The major determinants of the structure of material and thus of its properties are its constituent chemical elements and the way in which it has been processed in its final form, right? So if you know, this is what I have already talked about. I've taken an example of making a chapatis of bajri. For bajri, you don't need to put that dough so much. You can just mix it with water and then put little water and just put it on the fry pan or something like that. So have different processing techniques. Let us see again the historical perspective from different way. Materials are probably more deep-seated in our culture than most of us realize, right? So what are materials? Materials are like substance of which something is composed or made. Every segment of our everyday life is influenced to one degree or another by materials. Just take the example of mobiles. Earlier they were small, heavy. Now they are becoming thinner and thinner and being lightweight. Now, transportation, you can see transportation is very important. We have this aeroplane here, but we have other modes of travel also. Buildings, right? We can have tall buildings which are made in a month or two nowadays. Clothing, right? It is cold, so we are using cold stuff. But earlier it was like a thick blankets or jackets. But now there are thin, like, advertisement come thinner, inners we call it nowadays. Communication and recreation, all these are materials perspective and material things. Now, as we have already discussed, so the development and advancement of societies have been intimately tied to the members' ability to produce and manipulate materials to fill their needs. Now, when I say materials, we have already discussed. So material is a very inclusive term since it is the basic building block of all physical products. Materials are used in design and manufacture of products. Like you have polymers, as I already explained you, they are polycarbonate and some similar type of materials which are tough. Then we have composites. So these are basically polymers and there is a magnetic layer onto that. So layers of basically polycarbonate, aluminum, and acrylic, they are called as composites. So you have polymer, you have composites. Composite means mixture of 2 or 3 types of materials. Like you may have polymer, you may have some metal infused in the polymer, that are called as composites. Then you have ceramics, right? Ceramics are very brittle, or they're like, ceramic like porcelain, dish or jars, they all are ceramics. Then we have metals, right? And we have alloys, mixture of many metals or different materials. They are alloys. So here I can say we can distinguish or we can categorize materials into few types like polymers, composites, ceramics, metals, and alloys. Right? Now, what is material science? So basically, we need to see how they are cast, how to make them. Now, these chairs on which I had just shown, or on which we are sitting, or the plastic materials, or the molds, they basically are heated and they are put into certain cast. So that is called as casting. Metals are like forging, stamping, layer by layer, and other things. Then once this material is formed, they need to be processed, like texturing, temperature, time, transformation, heating it for a certain time, and all that. Right? So this is overall view of this material science. I'll go to the next slide, which will be better. So if you want to understand from the engineering point of view, and this all understanding the material science and material engineering is important if you are thinking of certain startup nowadays, right? So if you're thinking of certain startups, so you should know what material we need to take, how to check the material, how to characterize the materials, means how to do the analysis whether I'm getting this property or not. So in doing all this, we will come across these 4 pillars or these 4 points of this, right? So that is called as structure, processing, properties, and then performance. So you need to first decide what performance, what is your final product you are looking for. Then you need to see what properties you want your material to have. Then you can see what structure of the material will be and how will you process it. So these are very basic important things. So we can say that there is a relationship between structure and properties of the material. Designing the structure to achieve special properties of the material is very important. So these are the 4 important things, that is processing, structure, properties, and performance. Many applied scientists or engineers, whether they are mechanical, civil, or chemical, or any, they are exposed to design problem involving materials. Like see all this gear integrated circuits, right? You should have a gear which is integrated with a circuit, such type of buildings, such oil refineries, and then other computer applications. That is called as material science engineering, or we can call it as MSE. So a materials problem is one of selecting the right material from many thousands that are available. So criteria for selecting the material. So if you want to do any startup, if you're looking to make something new, so you have to first see like in service conditions, determine the properties required for the material. Now, any deterioration of material properties may occur during service operation. For example, significant reduction in mechanical properties. So you have to look for all that. Then economics, the most important one, right? So you want to sell it. You have a startup, you want to do social work, you want to create a good environment, you want to help people, you want to reduce the carbon footprints, but again, money is involved. So you have to also look for the economics, funding type. Okay. Now, as I've discussed all these materials, so now as I go back to this slide, this one, now all these are nowadays, they are doped or they are put by some materials that are called as special materials, which are called as nanomaterials nowadays. So we are moving to the second part of the talk, that is what is nanomaterials and nanotechnology, and which is very fascinating and the new upcoming field. Just to make you understand what is nanometer or how small nanometer can be. So if I take a meter means 100 centimeter. Generally we have a small scale. This, my palm length, so from finger to this end is 15 centimeter, around 15 to 20 centimeter. So you have 100 centimeter, that is 1 meter, right? If you see this small part of our hand, so that will be 10 centimeter. If I go and probe further with a microscope, so 1 centimeter will be the smallest part which we can see, 1 centimeter. And if I see the pores of my skin, so that will be around something 1 millimeter. And then, which we cannot see with the naked eyes, but if we keep some microscope, so we can see this type of structures on our hand. So this much distance is 100 microns, right? 100 microns, or here again 100 microns. And if I further probe, so 10 microns, so you can see white blood cells, right? So this is just for understanding. Now let us see, compare with different organic or biological materials. Like if you see any white blood cells or RBCs, so WBC and RBC, that is red blood cells, that's RBCs are circular and donut type structure. So they are from 5 to 10 microns, which we cannot see. And then we have this DNAs, which are around 100 nanometers. In 100 nanometers, you can have so many DNAs. DNAs are just 1 or 2 angstrom in small sizes, right? Very small. So this is just giving an idea. There is one more slide to give you an idea. So if you have an ant is around 5 millimeter, right? That is 0.5 centimeter. Human hair, as I said, is 10 to 15 micron. That is 10 raised to minus 50. It's generally not 10. It's generally into 50 to 100 micron. That is micrometer, the diameter of the hair, right? So if you take 0.1 micron, That means you have to draw 100 lines onto this, and one single line will be 1 micron. So micron means 10 raised to minus 6. That is 0.000001. Means 5 times 0 and 1. So small is 1 micron. And if you take a hair and put 100 lines onto the diameter, like, not diameter like this way, lengthwise. So that will be 1 micron. Imagine. These are RBCs. Then DNA is like around 2 nanometers, 2.5 to nanometers. If you see head of a pin, it is 1 to 2 millimeter. And if you see cellulose fibers or very small things, they are around 20 to 100 nanometer. Those who are in science, they know what is carbon nanotube, right? So rolled sheets of carbon or graphene, they are carbon nanotubes. So they are this small. If you take 5 atoms of silicon, it will be 1 nanometer. You cannot see atoms even with the highest efficient instrument. There is some way to see them, but very difficult. So this gives you an idea what is mean by nanometer. So nanometer means very, very small, right? We cannot see with even high-end instruments also, but we use TEM, transmission electron microscopes, and we can see them. Now, let us come to the world of nanoscience and nanotechnology and why I say it is very fascinating, right? So now we take the medicine, like we eat it through that, or we take injections. But we can make small injectable nanobots or nanorobots type of stuff, which will have certain like this. And the size of them is less than the diameter of hair, 10 or 100 and smaller than the diameter of hair. And they can specifically go to a particular virus or to a particular diseased cell, and they can catch it and they can crush it or bring it to dead form by attaching some chemical onto that or something, right? So if you see the view, it will be like this. And this has actually come into the General Electric TV commercial in 2005 and also inspired by Fantastic Voyage 1966. So already humans were from last 20 to 40 years were imagining all these things, and now we can see that they are coming to the reality also. Nanotechnology, before finding what is nanotechnology, before knowing what is nanotechnology, there is a famous lecturer, I will say, not scientist. He's a scientist, lecturer, everything. But we call him more in a physics like a lecturer because he was very good professor who used to talk and people used to write books on them. And his lectures are converted into volumes of books. Dr. Richard Feynman's volume 1, volume 2, and volume 3. In 1959, in Caltech University, what he told that you can write Lord's Prayer or Bible on a small, he told people that please tell me about miniaturization and how far it has progressed today. Tell me about electric motors, and there is a device on the market, they tell me, by which Lord's Prayer on the head of the pin. But that's nothing. That's most primitive. Halting step in the direction I intend to discuss. It is staggeringly small world that is below. In the year 2000, see what he's saying in 1959, that in the year 2000, when they look back at this age, they will wonder why it was not until the year 1916 that nobody began seriously to move in this direction. And he said, why cannot we write the entire 24 volumes of Encyclopedia Britannica on the head of the pin? And now it is possible. People have done that. And at that time, he had also made some prizes. Like if you write in small, I'll give you prize. So what they did, okay, we'll see that later, top, off and bottom. So, he said that this goal requires patterning on a 10 nanometer scale to write this 24 volumes. So at that time, it was difficult, but nowadays it's very easy. But just imagine the powerful imagination of a human being. Like Sir Richard Feynman in 1960 had said that this all is possible. What you're talking about writing the Lord's Prayer on a pin, you can even write 24 volumes. Nanoscience and nanotechnology. These are two figures, like both are in Mumbai, like Ajanta and Ellora, right? Elephanta Caves, right? If you go from Church Gate to the island, there is Elephanta Caves. And there is one in that Mumbai Gate, right? Gateway of India. These two are basically made in different approach. How this cave was made, a big stone or big hill was there, and they go on removing things from that, right? Second one was made by brick, right? So this was bottom up approach, and this is called as top down. मतलब बड़ा चीज है उसको आप छाटते छाटते छोटा करते जाओ, उसमें तराश के उसको अलग से करते जाओ, that is called as top down. और small thing से आप धीरे धीरे grow करते जाओ, that is called as bottom up approach. The same way nanomaterials can be made. So you can take a bulk material, you can go on crushing it or by some process, by some mechanism, and you can go on making it smaller. You can have nanoparticles. Just what we do in lab also. We take few chemicals, we heat them, there is a dissociation, there is ionization between them, the materials break into smaller things. So that is top down approach. We take bigger materials, we make small. We can also have atoms and atoms coming close and we can make it. So there are two ways. That is, one is called as top-down approach to make nanoparticles and one is bottom. So there are instruments, electron beam lithography. You can take an electron beam and you can make or pattern things, right? So photonic crystals using electron beam lithographic system. So you can see how much patterning is there. And you can see the size is very small, right? 10 micron. From here to here is just 10 microns. See, so beautiful patterning it has. So that is called as top-down approach, right? Now, taking a small thing. So here we have bigger thing, something you have, some plate, and then you are making holes into that. That is called as top-down. तुम तराश रहे हो उसको, उसमें से कुछ निकाल रहे हो. And this is bottom of approach. Atom carriers, all these are being made, right? You take atom and you go. Now, when you take nanomaterials or nano stuff, they have same thing, but they are different in color. You will be surprised to know, if you have not known what is nanomaterial, that these are the different forms of gold material. These all are gold at different sizes, right? So if you start from here, so they may be 10, 20, 40, 100, 150 nanometers like this. So when the size of the material changes, it goes down. What happens? The radiation, we see objects because the light falls on them and it comes to our eyes. So what happens? These materials are so small that their length is comparable to the wavelength of the radiation. And then the absorption and emission is different, right? And that's why we see different colors. So your white light is also made up of 7 colors, different colors. So these particles, when their size are different, so they are going to match to certain absorbance peak or certain absorbance wavelength of a particular light. And hence they will absorb that color and they will be looking like that. And which will depend on the wavelength of the light and their length. So imagine how human brain was. He had made minute particles by dividing gold. He had taken bigger gold and by chemically modifying in 1857, he has made gold nanoparticles. But again, my dear friends, my dear, I can say students or seniors, peoples, that before this only, long back, so many 1,000 or 2,000 years before we have this bhasmas in Indian tradition, Indian culture, or Ayurvedas or Unanis and all that, they all use this nanoform. You take homeopathy, Unani medicine or Ayurveda, right? Even the churches, old churches, they have this glass made up of same material, like made, but they show different colors. They are very ancient. So later on it was found that they are made up of same material but nano Ti2, titanium oxide nanomaterials. Their sizes are different and hence their colors are different. See, now why we should deal with nanotechnology? What is so important about nanotechnology? Why we should come into this now suddenly? Although we have come across a lot of theories of nanotechnology, and when we're talking about the startups and all, so what is so fascinating, what is so important? See, around 1850, 1800, it was textile era. Then India was invaded by foreign rulers and they took all their cotton, jute, everything from here. There was one time called as White Revolution. Later on, 1913, India basically, in the world everywhere there was transportation, making the infrastructure great. And then 1960-69, around this period, 1930 to 1970, it was automobile field. New cars were made, and all this stuff were made. Then we came across this 1980 to 1970 to 2010. It was computer, right? Here, I will again add that around the same period, around 2010 to 2005 to 2020, it is IT field also. So I can club this computer and IT, that is information technology. But remember my words, it's not my words, it is of all the scientists who are working right now and many companies, that nanotechnology is going to be the big thing, or it is already a big thing. You see all the labs everywhere around the world, 70 to 90% people are working with nanomaterials in some or the other. So 200 to around, this will go around some 40 to 50 years, right? So it will be introduction of technology, widespread adoption, and then end of that rapid growth. So maybe we don't know what we are going to do later on, but this will take another 50 years for us to grow, right? India can lead the world in nanotechnology in the next 10 years. India has got the brain power for this. What with its large pool of alumni from the leading universities, IITs and IIMs, and this is from Larry Pressler, noted businessman, consultant, former US senator. So imagine, everywhere you can use money. Even the robotics systems, it can be made lightweight, strong, and other things we have to use nanomaterial. But when we are dealing with this startup companies, if you're dealing with startup, you're thinking of that. So you can come across a concept called as polymer nanocomposites. So what are polymer nanocomposites? So basically you take a polymer, Now, all your clothes, polyesters, polyester clothes are made from polymer only. There are small granules, right? So they make into fibers, and that fibers are spun to make clothes. Or your chairs, or vehicle covers, or plastic bags. Everywhere there is plastic. But these plastics are normal. When you add nano fillers or nanomaterials to them, how much nanomaterials to be added? Suppose you have a cup of water, suppose. So you just drop one small grain of sugar into it. So if you have your polymer this much, then you just add one dot of nanomaterials into that. That will be enough to create the property enhancement, right? And there is rapidly increasing activities in nanoscience and technology, nanotechnology supported by sizable national programs, which has led to a variety of efforts in the development and understanding of polymer. The study in this area can redefine the methods used for developing lighter, stronger, high-performance structures and processes with unique and non-traditional properties, leading to exploration of high-strength and superior performance polymers, liquid crystals, and fibers. Just an example, I was talking about this, self-cleaning coatings. Self-cleaning coatings. The leaves are so clean. You see lotus leaf. Now we don't see much lotus leaves, but you see that aloo vadi ka patta rehta na, that is aloo vadi mein banate hain jo roll get wo patte rahe, or many leaves we see. They are self-cleaning. The nature has made them pores onto that nanostructured pores. So same type of structuring we can have. The special materials we can have, they have anti-graffiti. मतलब उस पे कुछ लिख नहीं सकते, आप धो तो निकल जाएगा. Heat shielding, electroceramics, fuel injection sensors we can have inside. Tribological coatings मतलब आपने उधर अगर आप किसी चाकू से भी मार्क करने की कोशिश की तो इजीली उस पे मार्क नहीं पड़ता है. Fuel cell batteries, polymer nanocomposites, anti-reflective displays, abrasive protections, hydrocoat solar cells, color switching, catalysts and nanoparticles in tires and all that. If you use, it have been running. I'll take half a minute. I'm thankful to Abhimanyu sir and to other organizer of this event.